Right, so let's begin with the discussion of the working of telescope, astronomical telescope to be precise. In any case, in the last lecture, we discussed about the Rayleigh condition for the resolution of two distant sources of light. Yeah, so let me give you a run through of what all we will be discussing now. The topics remaining, they are all JE mains topics. So they are all JE mains. So I want to wind up with telescope. Okay, so that we are done with optical instruments. After that, we'll be doing polarization of light. Okay, so that will complete the optics portion. Then we will come back to modern physics and we'll do semiconductors and devices, and finally logic gates, okay, and communication systems. In fact, communication systems may have been removed from your syllabus. I'll have to double check on that once on account of COVID. But in at any rate, all these topics we have to discuss up to here. So probably we'll be able to complete somewhere, probably beginning with semiconductors today or somewhere in between semiconductors. Let's see how fast we are able to go. Depends on that. Okay. So yeah, coming back to telescope. So as you know, it is an optical instrument to view very distant objects like stars, etc. Okay. So again, the instrument will consist of two lenses: the objective lens, the eyepiece. Okay. And what is happening in this situation is that the object is very far away. Okay. So remember we had discussed about the angular size of an object, okay, earlier. So that becomes important over here. So the ray diagram I'm drawing, the angles shown are exaggerated, but you have to understand that we are talking about very small angles here. So if these are the rays coming from a very distant object, so they are, the object's angular size is alpha. Okay, so these are incident rays from a very distant object. Okay, and its angular size is equal to alpha. So it produces an image on the objective lenses focal plane. It produces the first image I1 like this. That image is also of angular size alpha only from the point of view of the pole of the objective lens. With respect to the pole of the objective lens, okay, so this distance here will be the focal length of the objective lens. Okay. And if this distance is x, then we will deliberately adjust this situation in such a way that x is less than the focal length of the eyepiece, so that now the observer, the eye is looking into the eyepiece, and the eye looks into the image of I1 through the eyepiece. Okay. So next, when we trace the image of I1 through the eyepiece, the situation becomes something like this. So let's say this ray is going somewhere here. something like this, slightly divergent. So the image is the final image, the second image, say comes from producing these two backwards. Somewhere over here. So this I2 is the final image. Okay. So the final image I2, it has an angular size of beta, where this angle here is beta, okay, at the pole of the eyepiece. So you neglect the distance between the eyepiece and the eye. So looking into the eyepiece, you're seeing the angular size of the final image is I2. Whereas if you did not have the optical instrument, then you would directly be looking at the very distant object from the position where the pole of the objective is. Okay. So the natural angular size, that is without any instrument, without any telescope. So this is a very distant object. So you cannot bring it to your near point. Na? It's still going to be at infinity. So when it's at infinity, but your eye is directly in front of it. So your eye is where the pole of the objective lens would have been. This is that situation. Your eye is here and that object is at infinity. So the rays coming in, the optical size that they are seeing, that is nothing but alpha. So the natural angular size is alpha. Whereas the magnified angular size that you are seeing through the telescope, that is equal to beta. Okay, Aditya, I will summarize again when I complete this. Okay, so the angular magnification, as usual, the angular magnification becomes beta upon alpha over here in general. Okay, so in the case of normal adjustment, in the case of normal adjustment position, you want to keep the final image distance y should be tending to infinity. So x should be equal to the focal length of the eyepiece. Okay. Whereas for near field adjustment, you want y to be equal to least distance of distinction. So x will become that this kind of distance, okay, which we discussed about the microscope also. So accordingly, you adjust the distance between the eyepiece and the objective to get this range of. Okay, so as you know, the near field adjustment gives you the maximum angular magnification, and this gives you the minimum angular magnification, but it corresponds to the most comfortable viewing position. Okay, so this pretty simple actually. So just make a note of the diagram. Okay, so let us look at the specific formula for this maximum and minimum this thing. Okay, so now in this particular diagram, let me try and magnify this as much as possible. If the height of this image, the image I1, okay, if this one's height is some h, so let's say the height of image I1, suppose that is h, then alpha is equal to h divided by focal length of objective, because alpha is a small angle, so tan alpha is equal to, and beta is equal to this distance x, so h divided by x. So further we can make use of that. Okay, so here you're considering the triangle made by the image I1 with respect to this pole of the objective for the first one, and you're considering the triangle made by the height of the image I1 with respect to the pole of the eyepiece for your second triangle. So that's how we are getting this. So further we can, in a numerical situation, h will cancel out when we calculate this. So beta upon this thing will just become, beta is h by x, and alpha is h by focal length of the objective. So this becomes fo divided by x. So once again, you can see that for the normal adjustment position, the angular magnification, it becomes this ratio. Okay. And because you see an inverted image, so you can put it with a minus sign also, but basically the magnitude of the angular magnification becomes this. Okay. And in this case, the angular magnification becomes, just substitute this value. So f of the objective into d plus fe upon dfe, something like this, which if you take fe common here, you're left with a d inside, so you can write this as this. So you can see it is larger than the angular magnification for the normal adjustment position by a certain factor. So this is the maximum one, this is the minimum one. Okay. This is when the final image I2 is very far. So the eye is in the comfortable position. And this is when I2 is at least distance of distinction. So y is equal to d. So what you can do is you can just revise the whole concept of optical instruments once, from the beginning where we had discussed about angular magnification and the whole concept of angular size of an object, angular displacement of an object with respect to vision and all that. And from there, how we understood the concept of angular magnification by a simple handheld um convex lens, okay, or what we call a magnifying glass. And from there, the concept of compound microscope and then astronomical telescope, you can top it off with that. So you'll see that they're all interconnected and it's pretty simple, really. So anyway, this completes the optical instruments leftover part. Now we'll move on to the next thing in optics, which is part of our JEE main syllabus, which is polarization of light. Okay, okay, I'll give you some time to note it down. So I'm just going back to the previous section once. If you go through HC Verma or DC Pandey or something, you will find this derivation there also. And you will find a couple of extra things also, like terrestrial telescope, which also involves a third lens in between. And the purpose of that third lens is just to re-invert the image. So double inversion creates, an upright image, and also add another layer of magnification. Capital D is that least distance of distinct vision, is the near point of the eye. Okay, so hope you remember, Bhaumik, what is the value of capital D? Yeah, do you remember the value, Bhaumik? Yes, that's correct. Good. So that is your capital D over here. Is the near point of the eye. Okay, so let's move on to polarization now. Yeah, thanks. So this is related to the wave nature of light. So in that sense, it's a part of wave optics. So first of all, we have to understand the difference between a polarized versus an unpolarized beam of light. Okay, so polarized versus unpolarized light. Okay, so let's understand that. So any light that comes from natural source of light, like light from a star or light from any combustion process or light from any kind of sparking or even light from an incandescent bulb, okay, or light emitted by a diode or anything like that, which is coming from some kind of atomic level process, it is what we call unpolarized light. And let's understand what that is. Okay, so any light emitted from natural sources, example combustion, okay, etc., is a what we call unpolarized transverse electromagnetic wave. So let's understand what we mean by unpolarized over here. Transverse, we already understand. So what this means is that if this is the direction of propagation of light, and suppose this is our x-axis or whatever, okay, so this is the direction of propagation. Then at any point on the light beam, if this is your yz plane, okay, so this is your y-axis, this is your z-axis. Then at any particular point on your what we call light beam, the electric field and the magnetic field will be two mutually perpendicular vectors which lie in the yz plane. Okay. But in the case of an unpolarized beam, it is such that this angle theta is randomly changing with time. Okay. So for unpolarized light, okay, the electric field and magnetic field are perpendicular to each other at any instant. Okay. And lie in the plane perpendicular to the direction of propagation. But in that plane, they are continuously rotating. Okay, so they lie in the plane perpendicular to the axis of propagation. Okay. But they are not fixed along any axis. Okay. So they randomly rotate in direction. So they randomly change in direction. So that means in this case, at any given point on the beam, electric field at any point of time will be like this. It will be some cos theta k cap plus sin theta j cap, let's say. So magnetic field will be B naught minus sin theta k cap plus cos theta j cap, such that theta is randomly varying. Okay. So of course that will be then multiplied with the term sin this thing, omega t minus kx, and this will be multiplied with the term. So the amplitude of the electric field and the amplitude of the magnetic field, these are randomly varying with time. The direction of the amplitude is also varying with time. Okay. So it's like this. So the electric field amplitude is this whole term now. So it is of fixed magnitude E naught, but its direction is rapidly varying. The magnetic field's amplitude is this term, but it's rapidly varying. And at any point of time, you can see that E dot B is zero. Okay. So this is what happens in an unpolarized beam of light, and this is the type of light that comes from uh, this thing, the natural sources of light. Okay. Now, since the process of generation of light from atomic sources is driven by quantum mechanics, and there's a lot of complication in that, so we cannot really get into a theoretical model of why this happens. It's a bit like a black box. Okay, but we can relate to equivalent situation in the mechanical domain, and I'll explain that, and it will become clear why that happens. Okay, so another way to understand it is that if you are looking into this beam of light coming straight towards you, okay, so let's say you're looking into the YZ plane, so the x-axis is pointing towards you, then at any point of time the electric field will show up at one moment as a vector like this. Okay, next moment it would have shifted direction, next moment it would have shifted direction, next moment it would have shifted direction. So it will be anywhere in this plane. Okay, so the electric field's amplitude will keep rotating, and not rotating in any structured manner, that is going clockwise, anti-clockwise at some fixed rate, not like that, randomly. But of course, at any point of time, if the electric field is in a particular direction, then the magnetic field will have to be in the direction perpendicular to it. It will have to be in the 90-degree direction. So they are kind of synchronized in how they rotate. Okay. So if we want to understand this somewhat with a kind of equivalent situation in the mechanical domain. Okay. We can try and visualize that. An example of an unpolarized transverse mechanical wave. Let's see how that works out. So we have that same basic model to start with, that we have a very long string which is of a certain tension and linear mass density. Yeah, actually there is a principle for that. That is by the, you know, yeah, magnetic field and electric field will have pi by 2 phase difference, because what happens is that electromagnetic wave theory, na, the rate of change of electric field is proportional to the magnetic field, and the rate of change of magnetic field is proportional to the electric field. So they are propagating through induction. Okay. Anyway, so getting back to this, so if we have a long string which is at tension T and linear mass density mu, this side going to infinity. Now this end of the string, so this is our x-axis, suppose. So the point O, what we are doing now is that if at the end O of the string, okay, randomly transverse pulses are generated in the YZ plane. Okay, then what will happen at any point on the x-axis? Our direction of displacement will not be along the defined axis. It will keep varying in the YZ plane. So the wave propagated is such that, okay, the displacement at the random point P will not be along a fixed axis anymore. It will be such that the general displacement at this point P will become something in the YZ plane, into some kind of function of x and t. This will be, so any point P on the string will experience transverse unpolarized displacements in the YZ plane. Okay. So instead of giving this a structured, ordered kind of motion, where at the point O we did SHM, so this was some amplitude into sine omega t plus phase constant. So at the point P, the displacement was along the y-axis. It became omega into t minus x by v plus phi. So we're not doing this now. Instead, what we're doing is we are doing a random motion in the YZ plane at O. So what that does is it creates unpolarized transverse displacement at the point P. Okay. So you'll have some kind of an equation like this, where this equation obviously will be of this type if it's traveling in this direction. And all that. So this is the mechanical equivalent of unpolarized transverse wave. Okay. So now in electromagnetic wave, what is happening is that the disturbance that is moving is not displacement. It's not physical displacement of medium particles, but it is rather electric field oscillating and magnetic field oscillating. So if the electric field is oscillating at the source point in directions which are randomly varying in the YZ plane, then that oscillating electric field will generate magnetic field which is also varying with in direction. So from point to point, the propagation of electric and magnetic field, which is happening from changing electric and changing magnetic field, also does not have any fixed axis. No. They will be perpendicular to the direction of propagation, but they will not have a fixed axis in that plane. So that is how basically unpolarized beams work. Okay. Now there is a process by which such light can be polarized or such waves can be polarized. And once they are polarized, what happens is that the disturbance at any given point, whether we are talking about electric and magnetic field in case of EM waves, or we are talking about physical displacement of particles in case of mechanical waves, the disturbance becomes along a fixed axis. And when that happens, we call it the polarized waves. Okay. So polarized waves, the general definition of a polarized wave is a wave such that the disturbance at any point in the medium is along a fixed axis. So, for example, when we talk about polarized light, okay, let's say along the x-axis, it means that the electric field and magnetic field at any point, okay, oscillate along fixed axes that are mutually perpendicular in the plane. Just a Yeah, so the electric field and magnetic field at any point they oscillate along fixed axes that are mutually perpendicular in the plane, of course, that is perpendicular to the propagation axis. So in the plane perpendicular to the propagation axis. Okay. So an example of this would be something where our wave is propagating along the x-axis, and we have chosen our y and z axis as the particular axis along which the electric field and magnetic field are there. Okay. So the x-axis is the axis of propagation, and now what is happening is that at any point our electric field and magnetic field are oscillating along the fixed axis. So let's say the electric field is oscillating along this axis, and the magnetic field is oscillating along this axis. Okay. Which means that the magnetic field will, at any point it will go from this to this to back to this to this to this and back. So the magnetic field vector will oscillate between plus b in this direction and minus b in this direction. Similarly, the electric field vector will oscillate between plus e in this direction and minus e in the opposite direction and back. But they will be along fixed axis. So suppose those axes are the ones which we have selected as our y-axis and z-axis respectively. So in this case, what is happening? Our electric field will have an easier definition. It will be E naught j cap into that term, sine omega t minus kx, right? And a magnetic field will be v naught k cap. So this is just an example. The axis could be anywhere in the yz plane, but they have to be mutually perpendicular. But they are now fixed axis if they are polarized. So like this. So the amplitudes of the electric field and magnetic field are along the fixed axis. So that is an example of what we call a polarized uh, transverse electromagnetic wave. So this is polarized transverse electromagnetic. Okay. So now the whole question is, since polarized light does not exist naturally, okay, when light is created from atomic sources by emission of photons from electronic transitions, the light generated is not polarized, it is unpolarized. So how do we get polarized light? Okay. So there are various processes by which light can be polarized. Okay. The maximum effectiveness of polarization, that is the percentage of polarization, is maximum when light passes through certain materials which are called polaroids. So polarization, it is a process. Yeah, electric and magnetic field will oscillate, na, beta? So as you can see now, what is happening at any given in these equations, at any given value of x, at any given point, your value of x is fixed now. So your electric field vector is E naught sine omega t plus some phase constant j cap. So it's varying between plus E naught j cap and minus E naught j cap. So that's why I've shown the arrows like this. But the axis along which it's varying, that is a fixed axis. Okay. So the electric field is going between 0 to plus E naught to minus E naught to back to 0 like this. But it's not doing like this. It's not going like this. It's not rotating everywhere in the. That would happen in the case of unpolarized light. Okay, right. So hope that difference is clear. Okay. Yeah. So coming back to this definition, polarization is the process of converting natural unpolarized light into polarized light. Okay, so it is the process of conversion of unpolarized light into polarized light. So this can happen via passing light through a specific type of material called a polaroid, okay, or polarizing film. Okay. For example, the type of thing that is used in shades, okay, or 3D goggles even. So these are artificially created materials which have this effect on light or polarization. Polaroid camera works partly on the principle of polarization. So yes, it has a Polaroid filter uh, along with the lens. Okay. Second, polarization can happen because of reflection at a surface, but this creates partial polarization. So I'll explain what partial polarization also means. So this basically means that the electric and magnetic field are still varying in direction, but with dominant axis. So that means, for example, if the axis of polarization is the y-axis for the electric field, so the electric field in general will be in the yz plane, but such that the y component will be much more than the z component. It will be dominant compared to the z component. Similarly, polarization also happens, but partial polarization during refraction. Refraction also causes partial polarization, and that too different types of materials create different amounts of polarization. Okay. And also scattering of light causes polarization. For example, when sunlight, which is more or less white light, passes through the atmospheric gases, it creates scattering. So scattering is basically what that uh, photons from the sunlight are absorbed by the gaseous ions and then re-emitted. Now, in the process of absorption, photons of various different wavelengths are absorbed with almost equal kind of probability. But in the process of emission, certain wavelengths are favored over the others. Okay, because certain relaxation uh, energetics are more favorable in terms of probability compared to others. So that is why scattering of light always favors certain wavelengths getting emitted. So part of the reason why the sky appears to be blue is because of the scattering process. Okay. So scattering is not officially in our syllabus, so won't get into it fully. But as per your general knowledge, you can read more about scattering, and it provides an interesting explanation for things like this. So the main important one for us here is the process of polarization by passing it through materials called polaroids. So how do polaroids function? Let's try to understand. Okay. So what basically happens is that you have a beam of light which is coming from an atomic source. So if you look at the electric field, so we'll concentrate on the electric field only. At any point here, it is typically, if you superpose the electric fields at various different times, it's like this. So it's unpolarized. Okay. But now you make it pass through a material which typically in a diagram is shown like this. Show it something like a disk. So typically, if this is a polarizer with a sort of a mesh like this shown, so this is a diagram way of explaining that the axis of polarization for the electric field is this one. So whenever we draw a polarizer with a mesh like this, the direction of the lines in the mesh is the axis of polarization for the electric field vector. So if this is like this is the y-axis, then this is a polarizer which will polarize the electric field vector along the y-axis. So we call that the polarization axis is the y-axis. And by default, we are always talking about the electric field. Okay. So in this diagram, if this is my y-axis, this is my z-axis, this is my x-axis. So on the other side of the polarizer, the electric field that is generated will be just like this. It will be only along the y-axis. Okay. Now you might ask that why it so happens that once it's come outside the polarizer also it's still polarized. The reason for that is, see, what is happening is that for the disturbance over here, the source was the atomic source. So the source was generating electric and magnetic field randomly in the YZ plane. So those time varying electric and magnetic fields were inducing time varying electric and magnetic fields from point to point as you go along. So because the source itself was unpolarized, so the disturbance at any other point also became unpolarized. But the moment you look at the electric field produced anywhere inside the polarizer, so what the polarizer does is it does not allow electric field to be generated along the z axis. It allows electric field only to be generated along the positive x axis. So now, for the portion of the beam that is in front of the polarizer, the source of the disturbance itself is the em waves that are created, or the em field created inside the polarizer. So inside the polarizer, so again you're going back to Huygens principle. Any point in the wavefront becomes the secondary source for the waves in front of it. Okay, so all the points inside the polarizer, they act like polarized sources for the points ahead of the polarizer. So that is why the entire beam in front of the polarizer is getting polarized. Okay, and obviously there'll be an accompanying magnetic field which will be perpendicular, so that will be somewhere along the z-axis. But here, remember, for representation, we pay attention only to the electric field. So on this side of it, we get a polarized wave. Okay. So the mechanical equivalent of this, you can think of like this. That's also very interesting to consider actually. Example of polarization in the mechanical domain. Okay. So this time, this is a very long string which is going to infinity on this side. So tension T, linear mass. Okay, so this is a long string. But somewhere in between, we have placed, let's say, two vertical rods like this. Okay. And they are very close to each other. The vertical rods are very close to each other and they are fixed. Okay, like a grill. So the string is going through the gap between two fixed rods along the y axis, let's say. So now you can see what I'm talking about. So at the origin, if I create that kind of disturbance, random disturbances in the YZ plane, pulses in the YZ plane. So then I'll see that these pulses, they are all the time varying in position. So the displacement at any point is like this. But here the rods don't allow any displacement along the Z axis. They only allow displacement along the Y axis. So what we'll see is that the wave that is now on this side, that will be polarized. It will have disturbance only like this. It will not have this kind of random kind of displacement. So again, if unpolarized transverse pulses are created at O. Okay, and let's say where the two rods are present. This point is, let's say, A. So the transverse waves in the region OA will be unpolarized. Okay. But at A, because of the presence of the two rods, the displacement perpendicular to the y-axis is blocked. So the particles are forced to oscillate or displace only along the z-axis. Now those displacing particles only become the source for the points beyond the point A. So that is why beyond A on the string, the disturbance that propagates is going to be a polarized one, and it's going to be polarized along the y-axis. So some similar kind of process, which I will explain in a sort of example manner. Okay, yeah, it's just cancelled out, no? Because see, it's like this. No? You have those two fixed rods, and the string is threaded in between them. Now these are very close to each other, so they don't allow displacement in this direction. They only allow displacement in this direction. You're understanding this, people? No? Just imagine you have those two rods which are Imagine those two rods are very close to each other, okay, and the string is passing in between them. So it allows the disturbance only along this perpendicular direction. It does not allow the disturbance, okay, like this. So even if you create unpolarized disturbance on this side, the particles of the string which are wedged between the rod, they are forced to be allowed to move only along the y-axis. They are not allowed to move along the z-axis. Okay, so Anudeep, hope the point is clear. Yes, the amplitude, now see, in this case it is random, so it's going to be uneven. Okay, I'm going to come back to the case of visible light and all that. So there we'll see we have to do some averaging, and it affects the net amplitude, and therefore it affects the net intensity. In fact, that is one of the formulae that you'll have to remember, that how when we convert unpolarized to polarized light, by what factor the intensity of light changes. So we'll come to that. Okay, so that's a good point you picked up. That yes, the amplitude will be affected because of the process of polarization, because effectively you're cancelling displacement along one axis. Okay. So anyway, so coming back to this is unpolarized, but at E, okay, due to the rods, okay, the particles of the string are allowed to displace only along the y-axis. Okay, so therefore the wave propagating further ahead of that point A, that becomes a polarized wave, with the axis of polarization being the y-axis. Okay. So something similar happens in the electromagnetic domain, and it's actually quite an interesting situation how it happens. But basically, a Polaroid filter blocks out electric field along a particular axis and allows electric field only along the perpendicular axis. Okay, so in this case, if you want the polarization axis to be the y-axis, you have to create some situation where inside that particular Polaroid filter, something will cancel the z component of electric field and will only allow the y component of electric field to exist. Okay, so we'll discuss how that happens. Okay. But hope the mechanical domain example is clear to all of you. So it gives you a kind of visual idea, what is happening as the wave passes through a Polaroid, and on the other side of it, there is polarized wave generated. Okay. So now coming back to a sort of rough idea of what happens inside a Polaroid. Okay. So again, this is not from your textbook or your reference books. This is a little bit more in depth about the subject. So you don't need this for the exam level. I'll tell you what exactly you need, but it's an interesting subject. So just hear me out. Okay. So, Acha, you want me to scroll up? Okay. Yeah. So while you're writing down this part, we'll just continue with the discussion a little bit. Okay. So in electrostatics, you have understood how to cancel an electric field. Okay. If a region has an electric field, because of some presence of charge nearby and all that, but you want that at a particular volume or in a particular region of space there should be no electric field. How can you shield that region from electric field? You know this in electrostatics. Can anyone give the answer? Like, I have some kind of system of charge present here. So this is generating electric field lines like this. Okay. If it's positive charge, it's generating field lines like this. But I want a certain volume of space. Like I want, let's say, a region over here. I want that inside this region there should be no electric field. So what I should do? Yeah, but placing opposite charge will not, may not 100% work now. But what I can do is, yes, I can put that region inside a metallic shell. So that will shield, yes, a conducting shell. Okay. So what I can do is I can put a conducting box made of conducting material of any shape, like a spherical shell of metal or anything like that, and immediately that will induce charge in such a way, okay, that the electric field inside this region will become zero. So then the electric field lines will become like this. They will come and stop here. They'll come fold and stop here. But inside this region, now there won't be any electric field. Okay. So this is one way of blocking out electric field altogether. This is called the shielding effect of metals. So not only a solid metal has zero electric field inside, but a metallic shell also has zero electric field inside, provided there is no other free charge inside it. Okay. So you know this thing that if you take if you take a solid metallic block, okay, and it can be in the presence of charge, but the electric field inside it will be zero because that kind of induction will occur. But not only that, if you have a hollow metallic shell of any shape, even then the same thing will happen unless I separately place some charge inside. So this is a solid conducting body. Okay. This is a conducting shell. Any charge placed outside the shell, the region inside will be shielded from that in terms of electric field. Because again, there will be that kind of induction that occurs. Okay, so we all know this. Okay, but compare this to what we are trying to do. We don't want the electric field to disappear. We want the electric field to become along a fixed axis. Okay, so how do we do that? So that becomes a different thing altogether. So in the case of a Polaroid filter, let's say the axis being the y-axis, suppose. So I want this situation now that my Polaroid filter is represented like this. If this is the YZ plane. So what should happen is that inside this filter, okay, Z component of electric field should get cancelled. Okay, by something, some induction kind of effect, let's say. Whereas Y component of electric field should be undisturbed. Okay. So in other words, if I'm generating an electric field by some external effect like this, what should survive is only this. Only the Y component should survive. The Z component should disappear. Okay. So now think of this, that instead of a metal, if I had a very thin mesh, like a wire grill of thin metallic wires which were along the Z axis. Suppose I had this. Then what would happen in this region? Okay, that free electrons could distribute only along the Z axis. They cannot redistribute along the Y axis. So induction of charge can happen in which way? Only in layers which are parallel to the Y axis. Okay, so if I have, imagine a thin mesh of wires along the Z axis. Okay. So what would happen in this case? Only electric field like this can exist inside. Electric field like this cannot exist, because any electric field you create along the z-axis, there will be redistribution of charge along the z-axis, because free electrons can move along the z-axis. Okay, so inside such a region, inside this mesh, any Ez gets cancelled by induction. Okay, but any y component of field is unaffected, because there cannot be any redistribution of electrons along the y-axis. Okay, so this mesh will act like a Polaroid whose axis of polarization is actually the y-axis. So this occurs because free electrons can only redistribute by moving along the z-axis. Okay, so just as a demonstration purpose, okay, so suppose you have created an electric field like this. Okay, but the moment you put this electric field inside this mesh of wires, suppose like this, what will happen is that this electric field will push electrons in the opposite direction. So this will generate an internal electric field, an induced electric field, which is like this. So that induced electric field will cancel the z component of this and allow only the y component to remain. Okay, so the new electric field will come the vector sum of this external field and this. So the field remaining will be this. Okay, so the net field which will remain will be the sum of the external field plus the induced field. Okay. Now suppose the external field had some z component and some y component. The induced field will just become this minus Ez k cap. The electrons will keep redistributing till they don't need to move anymore. Okay. So we will be left with just Ey cap. Okay. So this is like a very, I'm saying like a very, hypothetical situation that you can create a wire mesh that is that thin and all that at the atomic level. So in Polaroids, actually, it is not metallic wire meshes which are created like this, but it is long chain organometallic molecules. And the outer electrons in the molecular orbitals of these long chain organometallic molecules are so loosely bound that they virtually act like free electrons of a conductor. So in an actual Polaroids consists of polarizing films are made of materials of long chain organometallic molecules. So these molecules act like the mesh, and electrons in outermost orbits act as free electrons. Okay. So if you research on the net, you will find the lot of literature about the process of synthesization of such kind of compounds and all that. It's all very interesting, and there's a lot of research behind it and uh, big industry behind it and all that. But in principle, at the atomic level, something like this is happening. Okay, yeah. So there are a lot of uses of polarized light. Yes. For example, the whole uh, 3D vision concept comes from polarization only. So I'll explain how that happens. Okay. So one of the applications of polarization of light is the 3D motion picture. Okay, but even before that, for example, LCD, liquid crystal display. It works on the principle of polarization. Okay, now next thing, effect of polarization on intensity. So if your unpolarized light, and I'm always going with the example where the axis of propagation is the x-axis. So there the electric field is something like this: E naught cos theta k cap plus sin theta j cap multiplied by that term sin omega t minus k, this kind of thing. Okay. Now you pass this through a polarizer with the axis of polarization being the y-axis, suppose. So what happens is that the z component of field gets cancelled. Okay. So what we are left with then is this E naught sin theta j cap into sin omega t minus k's. Now remember that theta is very rapidly varying. Okay, it's a rapidly varying thing. It does not vary with any particular frequency or anything. It's rapidly varying. So you can see that the amplitude of the polarized beam versus the amplitude. So this is the polarized light. This is the polarized light's electric field. This is the unpolarized light's electric field. Okay. So you can see that the unpolarized light has an amplitude which is mod of this thing. It is mod of this E naught cos theta k cap plus sin theta j cap. So the amplitude is nothing but E naught. Okay. So the amplitude is equal to E naught for the unpolarized light. But for the polarized light, what is happening? The amplitude is actually like an instantaneous term, E naught sin theta, mod of this, of course. Okay. So we take the average amplitude because it's rapidly varying as E naught sin theta mods average. So that is E naught sin theta's mods average. So this sin theta's mod average, you'll remember from AC circuits, is basically what? 1 by root 2. It's like the RMS value of sin theta. Okay. So mod sin theta's average is square root of sin square theta's average. Okay. So it is RMS value of sin theta. Okay, not for theta going in a cycle, but rather theta varying rapidly. But that will be the same as theta going in a cycle. So it's 1 by root 2. Okay, so that whole calculation you don't need to get into again, but you can understand. So this becomes, so the average amplitude becomes E naught by root 2. Okay, so if the unpolarized light had intensity I naught, let's say, which was proportional to E naught square. Now the polarized light, it has intensity I, which is proportional to this average amplitude square. So I becomes proportional to E naught by root 2 square. Okay, so from this you can see that the intensity after polarization becomes half. So because of polarization alone, there's 50% loss of intensity. So this is an important concept that you have to remember. You don't have to remember this entire method of calculation and all that. This derivation is not part of your board syllabus and all that, so you need not worry about that. Okay, but you have to know this as a fact. And in reality, of course, there is more loss of intensity because you're passing it through another material, so there'll be some absorption also. Okay, this is assuming that the transmission coefficient is 100%. Okay, and only polarization is happening. But in reality, there will be some more loss because there will be absorption also. Okay, so this is the first important formula, that when unpolarized light is polarized by passing it through a polarizer, there is 50% loss of intensity. Okay, so that's first and foremost as a fact you have known this. Okay, now the next thing which is very interesting, using a combination of polarites or polarizing filters. Okay, what happens if we use combination of polarizers? Okay, so for example, if we have two polarizers, so in the language of polarization, these are always shown by discs or ellipsoidal kind of shapes like this. Okay, but let us say that one of them has its polarization axis as the y-axis. Okay, so this one has, so let's say this is the filter A, which has the axis of polarization as the y-axis. Okay, and the other one has the axis of polarization as the z-axis. Let's say I'll change my system of axis. This is the z-axis. Okay, so my Polaroid filter B has the axis as the z-axis. Okay, now what happens if I take a beam of light and in its path I put this in series? So I have this Polaroid which is doing this. Okay, these are x-axis. So if this is unpolarized light, so unpolarized light we show like this, of intensity I naught. Then what will come out on this side is polarized light of intensity I naught by 2. Okay. Now if I pass this polarized light, which is polarized along the y-axis, through the second polarization filter, whose polarization axis is only the z-axis. Now what will I get on this side? I'll get zero intensity. Okay. So two polarizers with mutually perpendicular axes used in series. Okay. The combination blocks light. So this becomes an important concept, because what happens is that here the electric field is in the YZ plane, but here the electric field is surviving only along the Y axis. And this is going to block electric field along the Y axis. No? So there won't be any electric field left. Okay. So what the Polaroid filter A does is that it blocks the Z component of electric field. So this light now, this is polarized along the Y axis. And the job of this filter is to block EY. So there's no light that is left. Okay. Now, instead of them being mutually perpendicular, if they are at some angle, then that angle plays a crucial role in what is the intensity of light which passes through the combination. So, suppose now I have the situation where my first Polaroid is having a polarization axis like this. So, this one has the axis again along the y axis. But my second Polaroid, now this one has an axis which is like this. So, let's say it makes some angle with respect to the y axis. So this angle, let us say, is alpha. Okay. So what will happen now if I make light pass through the series combination of this? If the original unpolarized light is of intensity I naught, then tell me what will be the intensity of light after passing through the series combination. Okay. Given that this angle is alpha, so this one's B's polarization axis is at alpha angle with respect to y axis or A's axis. Okay. So what will happen here is if the incoming light is unpolarized of intensity I naught, okay, and electric field amplitude E naught, then here I will get polarized light along the y-axis, which will be of intensity I naught by 2, because the electric field amplitude will become E naught by root 2. Yes. But what about the factor now? That alpha will come into the picture. No? So see what is happening is that the output from A, it is having electric field like this, E1 j cap into sine omega t minus kx type thing. Okay. Yeah, let me see your answers. Yes, very good. So in the electric field, there's a cos alpha factor. So in amplitude, there is cos square alpha factor. Okay. So this becomes the input for B. Now what B does, okay, when this electric field, which is along the y-axis, is put into this filter. So what happens? This is the axis of polarization. So now which component will survive? This component will survive. Sorry, this component will survive. Okay, don't get confused with the mesh. Okay, this is actually the axis of propagation. Okay, so E1 cos alpha, this survives, whereas this E1 sin alpha is blocked. Okay, so when you input this into B, this cancels the E1 sin alpha component of electric field. So now my electric field becomes E1 cos alpha into some unit vector like this, which is this unit vector, into sine omega t minus kx. Okay, so this becomes my E2. Okay, so here the electric field that comes out on this side is polarized along this axis, and it is E1 cos alpha, or E naught by root 2 cos alpha. So the intensity I2 will be equal to I1 cos square alpha, or I2 coming out from this side will be I naught by 2 cos square alpha. And which is why if you put alpha as 90 degrees, I2 becomes 0. If you put alpha as 0, I2 becomes I naught by 2. So by varying that angle, you can actually adjust the amount of light that you're getting out from this side. So this is an interesting way of manipulating light. Okay. So this is what is used in a lot of optical instruments, where you have to control the amount of light coming out from each like pixel. So for example, in 7 segment display, you have these 7 segments. So actually what is happening, the entire screen behind is illuminated. But when you want to show the digit 8, all 7 of these segments have to be darkened. Whereas for example, if you want to show the number 0, then you want only 6 of these to be darkened. Okay. So it turns out that certain polarizer materials can be electrically controlled. So when they are under a potential difference, they act like polarizer, and when they are not under a potential difference, they lose their polarization. This thing. So your second polarization filter, which is at 90 degrees to the first one, if that is electrically controlled, so you can control when it is acting like a polarizer, when it is not acting like a polarizer. So you can control when it is blocking light, when it is not blocking light. So accordingly, you can control the 7 segment displays into showing whatever is required. So this is a very early application of polarization of light in electronics for 7 segment display in LCD. Okay, so this kind of thing also becomes an important formula. So basically, if you rotate the polarization axis through alpha, there's a factor of cos square alpha that comes in the intensity. This thing, that I2 is equal to I1 cos square alpha. So what has happened here is that the polarizer B has rotated the axis of polarized light, okay, from A, okay, of intensity I1 through alpha. So in the process, what has happened? The intensity becomes I1 multiplied by cos square alpha. I naught, of course, was unpolarized light. Okay, but if you start with polarized light of intensity I1 to rotate its axis of polarization by alpha, what factor of intensity gets cancelled out, or the intensity reduces by what factor? By factor of cos square alpha. Okay, so this is the basic idea about polarization. Now there are few more factual things we have to discuss, like Brewster's angle and things like that. Theoretical things. So we'll come back to that. So we'll take a quick break of 5 minutes. But the essential thing about polarization we have already covered. Okay, the change in intensity factor and this formula, the change in intensity when the polarization axis is rotated by alpha. This kind of thing. One more formula, which will be the Brewster's angle, we'll discuss immediately after the break. Then we are done with polarization. Okay, so just take a recess of 5-6 minutes. We'll come back after that. Okay, people. So let's resume. So we'll discuss about Brewster's angle next, which is a case of polarization by reflection. But before that, let's quickly, just as a general knowledge, not that it's in your syllabus, but discuss about 3D motion picture and how polarization works in that case. It's an application of polarizers. So, for example, our vision is 3D because when we look at any object, okay, we are seeing it from two angles. This is if this is where our left eye is located, and this is where our right eye is located. So our brain is mapping together two separate images, and that's how we. Okay, so three-dimensional depth perception, it comes because of binary vision in human beings, and mostly in all animals also. Okay. So binary vision means that our brain interprets two sets of images, okay, from left and right eye. Okay. Now the thing is, when we look at a normal photograph or an image, that is not happening. Okay, when we look at a photo of an object, our left eye and right eye. So see, the photo has been taken from a camera lens of an actual. So if the photo is of an object, okay, so that object has been photographed by a single lens. So that object was put in front of a lens and an image of that was created. Okay. So what is happening is that when we see that image through our left and right eye, there is no three-dimensional depth in it. Because what is happening is that our left eye and right eye are seeing the same image. Okay, that is the same reconstruction of that object taken from one angle. So there is no three dimensionality in it. Okay, so to create three dimensionality, what we need to do is we need to see an image of that object appear to be three dimensional. We need to first of all photograph that object from two cameras. Okay, camera one, camera two. Okay, so they'll create two different images, and now these two images need to be overlapped. But the problem is if you overlap these two images and put it in front of your eyes, now what will happen? Still we will not see any proper three dimensional. Still what will happen is that we will see a blurred picture. Okay. Why a blurred picture will be seen if you put it directly in front of your eyes? Because left eye sees both the images, one and two. The right eye also sees both the images. Whereas what you want is it should see only one image each. Now, in order to properly perceive the three-dimensional depth in it, what we want is that the left eye should see only what camera 2 has taken, so image 2, and the right eye should see only what camera 1 has taken. So that is where Polaroid comes in. So what we do is in the projection of the images 1 and 2, okay, let's say image 1 is projected with light having polarization along y-axis, okay, and image 2 is projected with light having polarization along the z axis. Okay, And now what you do is you wear shades on your eyes. So your left eye, your right eye is in front of, now this one is in front of a Polaroid which is along the y-axis, and this one is in front of a Polaroid which is along the z-axis. So what is happening? Your left eye will see only which image? It will see image 1 only. Image 2 is blocked out of it because the light coming out from image 2 is polarized along the z-axis, and this is not, this filters out the light along the z-axis. No? And similarly, your right eye sees only image 2. Okay, so that is how you are able to perceive two different images with the individual eyes, and that is why when you take the Polaroid glasses off, you see a hazy picture, but when you put them on, you see the proper three-dimensional picture. So this is the actual application of polarization in 3D motion photography. Okay, so hope the concept is clear. You can, see some videos and all on YouTube which will explain this with animations and all also. But this is the basic idea of polarization, how it is used in three-dimensional motion picture. Motion picture is just images coming one after the other in motion. So then they become a series of events instead of a single event. So there's a timeline for events happening. Okay, so next we will move on